Okay, let us jump into day 9. Disk Fragmenter. He shows you the disk map, your puzzle input that he's already generated. For example, so big string. The disk map uses a dense format to represent the layout of files in free space. The digits alternate between indicating the length of the file and the length of free space. So disk map like 1, 2, 3, 4, 5 would represent 1 block file, 2 blocks free space, 3 block file, 4 blocks, blah 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 blah. 90909 would be super dense, no space. Each file on disk also has an ID number based on the order of the files as they appear before they are rearranged, starting with ID 0. So this map of 1, 2, 3, 4, 5 is 3 files, and 1 block file 0, 3 block 1, and a 5 block 2. The first example above represents these individual blocks. 2, and then 3 space, and then... But this must be longer than what we're showing here, right? Maybe not. The MP pod would like to move files 1 block at a time from the end of the disk to the leftmost free space block. So we're moving things around. This bigger one is a little bit harder. The final step of this file compacting process is to update the file system checksum. To calculate the checksum, add up the result of multiplying each of these blocks' position with the file ID number it contains. If the block contains free skip it instead. Oh my goodness, this is complicated. Continuing the first example, the first few blocks position multiplied by its file ID number is 0, 1, 2, 3, 9, 4, 8. Single very long line. So 0, 0. I'm actually confused about this final bit. To calculate the checksum, add up the result of multiplying each of these blocks' position with the file ID number it contains. Okay, so 0 contains the 0th file, and then 1 contains the 0th file, and then 3 contains, or 2 contains the 9th file, 9, 8, so on. Okay. So, this is kind of in a few parts. Are we just going to sort of do what they've sketched out here and sort of implement it? So step 1 is to take this and expand it out. Then compact it, and then we need to keep track of what file is in what spot. Or empty. So we'll take from the back and move to the first empty space. So we can have like an index basically, and move those around, and just like a big array where we're like shuffling stuff. Basically like replace this and put it here. That could work okay. And then we can compute this where, yeah, we replace each block with like the file ID, and then we can move the file IDs around, and then we can shuffle the things around. So like this could be like 99 or something in this block because the file IDs will like be bigger than a single digit. But we'll probably implement that for now. So I think we basically just like do what they've sketched out here. So first thing is like taking this and parsing it so you understand like the alternating flip-flop is like file free, file free, file free, blah, 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 blah. And we're going to slowly build up a big array of empty space in files. And we can assign them identifiers and we just like keep putting them, appending bits to the end of the array. Okay, so let us get started. Okay, so given an input string that is a single line long, expand it out to the, I guess we can call this like, we go from like the dense representation to the expanded representation to the full disk layout. This is done by alternating, adding blocks to a disk array. Each number represents the number of blocks. We have we track the current file ID when it's data, if it's a file, and increment it every time. So we're going to basically end up with an array that looks like well, like the first one here is like the 0th file, so we'll have like 0, none, none, 1, 1, 1, none, none, like that, basically, where none represents is free space, and the integer represents the file. Next, we find the first free block and save the index. Then we start from the right and swap the free block with the one on the end. Then increment, then find the next free block and decrement the right side until we find the next used block and repeat until the two indexes are equal or off by 1. Finally, we calculate the score by multiplying the index in the disk with the file ID and sum them up. Okay, so we don't actually need sys because we're just going to get our, no, I guess we still do. We'll leave this here, but it's actually just the one line basically. Yeah. Okay, so step 1, let's do the parsing out. For I char and enumerate raw.strip. Disk is equal to this, and then we're gonna like flip-flop free equals false. So 2 says we put 2 here, int disk map. So we have files in free space. Okay, there's also an ID. File ID starts at 0. Yep. This isn't the character, this is like the size basically, right? So size equals int size. We're going to append if free, then disk dot extend by none times size, else disk dot extend file ID times size, and then free is equal to not free. And if this was the case, file ID increments by 1. Why am I keeping the index? I guess I don't need it. I thought I would. And then let us print out the disk to make sure that we're getting this right. So we have 0, 0, and then nuns, 3 nuns, 3 nuns. It's too many nuns. No, 3 nuns, 3 ones, 3 nuns again, and then a 2, and then 3 more nuns, 3s, nuns, 6s, nuns. Okay, cool. So it seems like that expansion, or the initial parsing and expansion piece is working. So now we're going to do our like loop, where we scan forward until we find the free. And then we're going to scan from the right until we get some data. And then how do we know when to stop? We moved the 6 into the final free spot, and then if we looked for the next free spot, it would be equal to or it would be greater than the next spot that has a digit. Okay, so we can do that basically. Free index is equal to, I want the Python to find the first Python find item, find index of first index of value in a list. Index. Okay, that's nice. So disk dot index of none. Let's make sure that's working properly. Is that 2? Yep, that is correct. And then we want to find the first non-none, the index of the first non-none value starting from the end. Is there like an elegant way to do this, or can we just like bang something out? with a quick scan or something? Sure. Um, free index, and then what's this other thing called? This is our like uh, move index equal to disk minus 1, while move index is not equal to is equal to none. Move index equal to oh no, this is supposed to be the index, not the value, right? So we can say minus 1 actually, and then while disk of move index equal to none, move index minus equals 1, print. Hmm. Do we actually want to use minus 1 here? No, I think we want to just do len of disk minus 1. 41. I think that's fine. I think that's fine. Yeah, that looks fine. Okay, and then we have this. So we've set up our things here. While move index is greater than free index, we're going to do some swapping here basically. So disk free index is equal to disk move index index disk at move index is equal to none. Disk index, no, free index increment move index decrement, and then print the disk again. Oh, we did something weird here. So good thing we are checking this. Why is there a none here? Oh, because we're not just incrementing, we're finding the next free bits. Right, so we basically want this again. Okay, so while disk of free index is not equal to none, decrement that, and then while, or increment that disk of move index is equal to none, do that. That looks better. Is that what we have here? 0, 0, 9, 9, 8, 1, 1, 1, 1, and then we have 5, 5, 6, 6. And there should be a 6 before some of these 5s. Cool. Okay, so that seems to be working. Now we just do a little reducey-deuce here. Does Python have reduce? Reduce function iterable. Accumulate. See, this is so much more elegant in other languages. Whatever. total equals 0 for I block in enumerate disk total plus equals I times block if block equals none, break was block, and then print the total. 1928, that is correct. Save this. A lot of nuns and some values. Okay, cool. Delete this, delete this, delete this. Okay, so we got a lot of while loops, kind of very C-like Python, I think, but pretty clear what we're doing. Okay, so this is just a matter of like reading through and understanding what's going on. Part 2. Upon completion, two things become immediately clear. Instead of moving individual blocks, you'd like to try compacting the files by moving whole files instead. This time attempt to move whole files to the leftmost span of free space that could fit in the file. Attempt to move each file exactly once in order of decreasing file ID number, starting with a file with the highest file. If there's no span of free space to the left of a file that is large enough, the file does not move. So the 9s fit perfectly, but 8 doesn't fit. But then why don't we just stop when we can't move any of these? No, we try to find, oh, because there's no space for the 8s anywhere, so we're scanning the other way. The 7s we look from here, nope, okay, this one would fit here, so we put the 7s in. The 6s can't. Why can't the 6s fit here? Or the 5s? Oh, because it's effort. So that we try to move the 6s, they can't fit. The 5s can't fit. The 4s can fit. The 3s can't fit. But the 2s can fit. And now we have a different checksum. So, how is this going to be different? Instead of just doing block at a time and doing the two moving pieces, we basically need to scan and be able to count the contiguous none blocks. Potentially, could we store those differently so that it would be a little bit faster instead of like counting the sizes, or do we want to just like keep doing loops and counting start and end indexes? I'm not sure. I am not sure. So how would we implement the other one? So we need to know the sizes of the files and the free spaces. So we potentially we can write a little count function. Yeah, let's do that. We'll write a little count function. Um, you can count from the left or the right. Hmm. we can remember how big these things are and where they start. When we're doing our first parse, we know when they start, and so we can have a dictionary that has the start and end indexes um, in a dictionary by file ID. We really need we do like spans where we could like give a given thing, or we could put the. How could we do this? What I'm thinking is, as we're building this up here, we could be building up a different data structure that's like a different representation of the disk that is like a list, but it's the size and the file or none, basically. And then how is that going to work as we update stuff? That becomes a little bit more of a pain. We're going to scan through, so we're going to files to the leftmost span of free space, the blocks that could fit. So we're going to have to scan basically all of the free space in order to see if it fits. So we could have one that's like the free space. And one that's the other one, and then we can like move stuff around and like splice bits in. I don't love that. I feel like I feel like it's going to be the best way to go. So, um, so the algorithm is like try to move each file starting from the right and going in decreasing order of file ID. But try to move the to a move all of each file to a free span of blocks looking from the left. If no space is found, move on to the next file. This is different. So this is all different. So, but what is our actual implementation here as we go through stuff? We want to know the start and end index. Not the length or start and end of each file. We want the length and location of each block of free space, and we need to be able to update the free space. So we go. We want the length, so it could potentially work to have our location map of the files initially, and then we just don't update that. But the free space one we do update as we go through it. And what's a good representation of the free space? Like one version could be a list where we have like start, end, start, end. Maybe we just have size and start. Don't need the end. And then basically we can like filter the list. And then to update it, we can basically just do like update, replace one of the elements with the new size and start location. Do we need to check? Would you need to do any merging? Potentially, yeah. Do we? I don't think so. I think if we move this in here, we'll never move this and end up with like more space afterwards, because once we've... Is that true? 2's going here. Basically, I'm worried that once we move, if we could move 555 over here, we would have 5 things here. 9 goes here. What if like 8 had fit somewhere? No, because we're always moving things over. So, and always reducing the amount of free space. So I think that's fine, actually. We should be okay with this. Yeah, so I think we do the same thing here. We actually have two of these maps that we're going to go through and update things as we go, or drop them. So we have our disk, which is where our actual representation is, free file ID. So I guess this is, well, we already used index. That would be the database term that I want to use here. We can rename index to pointer or something. So our file index is a thing, and our free index is a thing here. So if it's free, then we're basically going to free index dot add the size and the length of disk at this point, which is where we're starting from, right? I think so. File index. Yeah, that seems right to me. So we're saying we have two starting at 0. Yep. Oh, we actually also need to know the file ID here. So file ID, size, length. 0 is too long and it starts at 0. 1 is 3 long and it starts at 5. Yep. And then we have 3 free space starting at 2. Yep. Okay. So this seems correct. And then we're going to loop over these for file ID, file size, file start, and file index. Am I doing this right? Let me just make sure I don't have to unpack tuples differently. Nope, that's fine. Okay, so what we want to do is for free size, free start in free index. If free size is greater than or equal to file size, then we break and we say that we found something. Like, want to shadow these. That's too bad. I don't think I can say print. Is that gonna break for me? No? Interesting. 040, what? Hmm? What's going on here? Free size is 0 for number 40. Oh, because, yeah, this is unbound. Right, right, right. That does make sense. It's potential that we don't find anything. Um, found size, found start equals none. Okay, so if we find it, then found size equals free size, found start equals free start break. If not found, continue. So we skip there. Assert found size, found start. Okay, so once we've found them, we can move them. So step one, we need to move the file ID number to the other spot. Then we need to update, so we need to move the file on disk. So disk from start to start plus file size is equal to file ID times file size. So move the disk on the file, remove the old file, disk, file start to file start plus file size, and these may be off by 1, is equal to none times file size. Move the file on the disk, update the bit here. So we need to know which block it was. Found index, index. Free index. Enumerate free index. I don't know why this is upset. Int is not iterable. Oh, right. Yeah, okay. If found index is equal to free index index. Okay, the free index at found index. If file size is equal to found size, then just delete this item. Otherwise, we can update it. Free index is equal to the new size, which is found size minus free size, and then the new start location, which is found start plus file size. Found size minus file size. So we remove that much space and then we increment the thing there. And then we do our whatever. Found index was none. What? What? Oh, if... What? Assertion error, line 66. Found index. Found index is none. If free size is greater than or equal to file size, this doesn't make any sense at all. Print setting. Setting found index to 0. Hmm. saying false is annoying. So that's what was going on there. Okay, what is happening now? We're updating things, but we keep thinking that we're finding stuff at 0? That doesn't make any sense. Rent-free index. That's fine here. Let's print the disk as we go. None, none, 0, 0. That's not right. Oh, because we need to do this backwards. 260, is that correct? Not at all. 0, 0. Okay, here's the last one. 0, 0, 9, 9, 2, 1, 1, 1, 7, 7, 7, none, 4, 4, none, 3, 3, 3, none, 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 5, 5, 5, none, 6, 6, 6, none, 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 8, 8, 8, none, none. 260. Oh, because we didn't need to stop here. Continue. 2858. Okay. That looks correct. Stuttered for a second there, but that wasn't so bad. That's not the right answer. It's too high. Okay, interesting. Too high. So we've done something wrong that isn't obvious from what we've done so far. So are there any little mistakes here that could be obvious? 2 9s at the end. Are we calculating it wrong? Decreasing file ID for the highest. Okay. I'm just trying to think. What could be happening here? What could we be getting wrong? We're going to give it 5 more minutes and then we will stop. Attempt to move the whole files to the leftmost span of free space. blocks. Attempt to move each file exactly once in order of decreasing file ID number, starting with the file with the highest. If there is no span, the file does not move. Okay. I did something before where this, like, when we're replacing slices with other things, is that we actually changed the size of the disk subtly. So let's make sure that we're not doing that. Assert len of disk is equal to disk size. Okay, so that wasn't it. Are we fragmenting our free space, or our free space somehow? Print. So that it's fine here, but not in real, in a more complicated one. Ooh, okay. Okay, so we have this, and then this one should never be a problem. We don't actually need to add that one here. That's kind of weird, right? So they delete it from here. Is that right? This is how big it is and where it starts. No, this is slightly wrong. How is this working? It's the size and the length. One starting at 4 is incorrect. Very incorrect. 3 starting at 8 is correct. 3 starting at 12 is correct. 1 at 18, 1 at 21. So this one is wrong somehow. The first one we add is wrong. Why is the first one wrong? So it should say 0, 1, it should be 3 starting at 2. 3 starting at 2. Do I need to, is this off by 1? What is going on here? Size 3, disk is 0, 0, length of disk is 2. Oh, is this before? Yeah, this is before I've after I fragmented it once. Okay. Not crazy. Yeah. 3 starting at 2, and then 1 starting at 4. 0, 1, 2, 3, 4. Is there some point where I need to make sure that I'm not moving something that shouldn't be moved, I wonder? Yeah, I think that might be it actually. That's maybe our bug here, is we're not trying to just move it to the nearest free space. We're trying to make sure that we're not moving it somewhere that it doesn't need to be moved. And if we moved it in some files further on, they'd have higher indexes. So we need to stop at some point. If not found, continue. If free start is greater than file start, break. We'll just skip. Found start. That's still the same. This number looks smaller. This number looks smaller and is correct. Okay, cool. I am going to leave it there. Good night.